Okay, hello everyone. This is a video for the part one of our lab 4. So the purpose of this lab is to program function calling in assembly language. I know we have not yet covered how to write functions in assembly and how to call them in our lectures. That's why I will provide you the background, necessary background, which is needed for this lab. So don't worry about that. Uh, and for this lab, you need as a hardware, the hardware components you need is only your Arduino Uno board and the US cable for charging and data transmission to the board. So let's first cover the background and then I will explain the tasks. So the first thing is like how we can call a function in assembly. So in assembly of ATmega328P microcontroller, we have an instruction which is named as call. So the syntax of this instruction is call the name of the instruction and then the name of the function to which we want to make the call. In other words, the calling function name, right? So whenever you want to call a function in your program, you just use this instruction. So for example, if you want to call the function foo, so you will just say call and then the name of function foo. Okay. So then when you are writing the body of the function, so you must save any registers that you are going to modify within the body of that function. And then once you are done, then you must restore those registers from the memory before returning from that function. So a typical function body will look like as follows. So in assembly, so a function is just a label. So you will first save the registers that you are going to modify in this body of this function. You will save them on the stack. What is stack? I will explain it in a moment. After saving the register, you will do whatever you are supposed to do in the body of the function. And then once done, you will restore the saved registers from the stack, and then you return the execution control back to the caller function. And for returning, you will use the return instruction, which is written as RET in the assembly of the microcontroller. Now we said that we need to save the registers to the stack and we need to restore them from the stack. So what is stack? So stack is a data structure which is used to hold data temporarily. Temporarily, it follows last in first out order, which means that the element which you have placed on the data structure, uh, in the end, they are retrieved first. It will become clear when I explain how the stack works. So we use the name of push operation for putting data items on the stack, and pop operation. Pop is used to identify the operation of popping out or retrieving the data items from the stack. So depending on implementation, a stack may grow upward or downward in size. For example, in our microcontroller ATmega328P, stack is maintained in memory starting at address this one 0x08FF. It is of size 2 kilobyte and it grows downward, not upward, right? So, and push and pop instruction are used to place and retrieve the data items from the stack. So let's use the following figure to understand the operation of stack. So let's say you first push three values 1, 2, and 3 in three registers R16, R17, and R18, not push. Let's say you load these values. You load 1 into R16, 2 into R17, and 3 in R18 using load immediate instruction. So I have labeled these instruction with numbers just to indicate how the program executes in sequence. So first these three instructions are executed 1, 2, 3, and then we have fourth instruction in our program which says push R17. So what is the meaning of push R17? So remember we said our stack starts at 0x085. So in microcontroller we have a processor stack pointer. At this point we are not going to do anything special with the stack pointer, but I just want to inform you that there is a register which is named as stack pointer or SP, which points to the current location of the stack. Current location mean when we say push R7, the location in the stack or address in the stack, memory address where our data of R17 will be placed. So R17 has value of 2, so 2 will be placed on the stack at this address, and then stack goes downward. Next time, when fifth instruction says push R18, so SP is decremented. So before that, SP was 0x8FF. Now SP is decremented to 0x8FE, so it points to the next location downward. So now when you say push R18, so as a part of executing push, stack pointer is decremented, and then the value of R18 is placed in memory at this address. 0x08FE. So it now holds the value of 3. Now in next instruction 6, when you say push R16, again first the stack pointer is decremented. Now it points to the location in memory which is 0x08FD, and then the value of R16 is placed in that memory location. So that's why now it holds 1. So now we have seen how the register values are pushed on the stack. For popping them or retrieving them from the stack, we use the pop instruction. So let's say our seventh instruction says pop R16. So now what will happen, that the value which is currently pointed was pointed by the stack pointer. So what was the stack pointer? Stack pointer was 0x08FD. So when you say pop R16, so value from this location is moved into the R16. Now R16 holds 1, and then after moving the data from the location which is pointed by the stack pointer and putting it in the register, after that the stack is decremented, now which I have shown in the figure by using this red arrow. Now stack pointer points to 0x08FE. Okay, now in next instruction, instruction number 8, when we say pop R18, so the stack pointer is pointing at 0x08FE, right? So now the value from this location is loaded into the register R18. So R18 has now 3, and after loading the value into the R18, then stack pointer is decremented. So now stack pointer points to the location at address 0x08FF. Now in next instruction, when you say uh, pop R17, so the data from the memory location which is pointed by the stack pointer, which was 0x08FF, that data is loaded into the R17. Sorry, I made a mistake here. I should have placed like 3 is loaded. Sorry, what we are saying. Yeah, so again, let me track back a little bit. So ninth instruction, when we say pop R17, so what happens that the stack pointer was pointing at the address 0x08FF. So the value from that memory location is loaded into register R17. And I made a mistake here that I haven't indicated that 2 is loaded in R17. Otherwise, everything else is correct, right? And then the stack point is decremented, and so now it points to 0x0900. And if you note, I have shown this address in red because this is the lower limit. After that you cannot write on the stack. If you try to write, you maybe your compiler will complain, or your program will get corrupted. So most probably compiler your assembler will not complain and your program will get corrupted. So you need to make a check whenever you are decrementing your pointer, that stack pointer, that it values doesn't go below, it doesn't goes up 0x8FF, right? So this is the way how you can pop the values from the stack. So we have now seen how we can push and pop values in the stack. So remember that whenever we implement the functions that are going to modify any registers, we first push those registers on the stack, do our job, whatever we want to do in the body of the function, and then restore those registers from the stack before returning from the function to the caller. Okay. Another thing, as a part of the background information, is delay function, which is provided by Arduino API. So we are going to use this function in our this lab. So this function basically it allows you to wait for a specified number of milliseconds, and then after that it continues the execution. So the required number of milliseconds, for example, if you want the delay function to wait for 100 milliseconds, so you need to give that information to the delay function, the parameter, for example, 100 millisecond. And how you do that? By putting the value amount of like how long you want to wait, by putting that amount or that duration in the registers R22 to R25, such that you put the least significant byte of your required, like your value in R22, and most significant byte in R25. So let me explain it with an example. Let's say we want to use this function delay to wait for 100 milliseconds. So first what we do is that we convert 100 to hexadecimal form, which is this number. Uh, so all zeros and then 3E8. So now what we need to do is that we first need to load this value into the registers R22 to R25. However, before loading, we first push the current values of R22 to R25 to the stack, because maybe because we are going to modify those registers. right? And maybe they were used by some upstream code in our program. So we push their current values in this on the stack, and then we load this value R0x, R038 to R25, R22 to R25. So we load the least significant byte, which is E8, 0x E8 in R22, next byte, which is 03 in register R23, and then we load these four zeros in R24 and R25, right? And after that, we call the delay function by simply writing call delay. So delay implementation of delay is already provided by Arduino API. So we don't need to worry about that. And once we are done with that, after this is completed, so we need to pop those registers values which we pushed on the stack by saying pop R25, R24, R23, and R22. Remember that stack follows the last in first out order, which means that whatever you push on the stack and in the on the stack, you need to retrieve it in the reverse order. For example, when we are pushing, we are saying push R22, R23, R24, R25. So R25 is the last to be pushed, but when we are retrieving, so we retrieve in the reverse order. We say pop R25, then R24, then R23, then R22. Okay, so this was the background information. Now what is the what is the task one? So uh, for task one, what you need to do is that uh, so in task one, what you need to do is that first download these two files which are provided, and then open this .ini file, code skeleton task one lab4.ini file with Arduino ID, and save it as lab4 task one. Then add the encode.s file, which is also provided to your sketch lab4 task one from the menu bar. You know by this time how to add files. Rename your encode.s as encode underscore task1.s, and then connect your Arduino board, select your right Arduino type of Arduino board, and select the right port from the tool menu. You know all these steps, but now you need to compile and run your completed code after completing all the nine to-dos which I'm going to explain. So I already have this code with me, so let me explain what are these to-dos, or what are the things you need to do. So let's start with our code skeleton task one lab 4, uh, and here at the top I have defined and I'm telling assembler that there is a function named encode Morse, which is defined in the encode.s, uh, and then I have this function read two-digit value, which we will use in task 2. It is the exact same function as in our previous lab. So actually, you can also uncomment these two lines if you want, because we will need them in the task 2. And then in the setup function, we are just calling encode Morse, and in the loop function, we are just saying delay 20,000, and then after this delay, keep printing the stars on the serial monitor. Okay, so before I go and explain what is your job or what is your responsibility in task one, let me first explain the Morse code. So Morse code is a way of communication where we encode each character using by sending signals, and we send two type of signal. One is named as dot and the other is named as dash. For example, if you want to send a character A, so you will send a signal dot and the dash. In our program, we will indicate dash by blinking the light for a longer amount of time, which is like 100 millis, not blinking, by turning it on for a longer amount of time, which is 1000 milliseconds. So in other words, 1 second. And we will represent dot by turning on the LED for shorter amount of time, which is 500 milliseconds or half a second, right? So if we have the functions which can actually turn on light for one, which can turn on for give me 1 minute, and I uh sorry for the interruption. So where were we? Yeah. So if we have mechanism, yeah, how we are going to represent dash and dot in our program or in our lab? We will represent dash by turning on light for a longer time, and dot longer time in 1 second, and dot by turning on the same LED for short amount of time, which is half a second or 500 milliseconds, right? So uh, so we have this function encode mores, and in this function, what we are going to actually do is that we are going to encode the string go eggies, right? So let me explain to you this assembly file. Uh, so this assembly file is like partially completed. You need to fill in the gaps. So we are starting with the text segment, and we are making this variable or this name global so that we can use it in the .ini file and code Morse. And here what we are doing is that we are initially configuring our port B pin 5 as output pin, which is basically the pin 13 on your uh, Arduino board, pin D13 on Arduino Uno board. And there is an LED on the board, which is a built-in LED, which is already connected. So you don't need to externally connect any LED using breadboard. We don't need to do that. So what here we are doing is that we are first configuring that pin as output pin. Remember, the port B can be used both for reading as for in input mode or output mode, but we are saying that we want to use it in output mode. And then so this is actually a start of the body of the function, and then we are saying call encode G, because we want to uh, we want to encode the string go eggies. So here I can comment actually performs Morse encoding of string go eggies, right? Without encoding the space. Okay, so GOAGGIES. Okay. So then in the body of the function encode Morse, we are saying, okay, call encode G, which is another function, right? And then I have implemented already this function, but then you also need to implement other functions like encode O. So for example, encode G is basically, if you go to the Wikipedia, so for G, the Morse code is dash dash dot, right? So it is here, you can write dash dash dot. So and for the Morse code for O is dash dash dash. For other, you can go to the Wikipedia and you can check the Morse code for A and I, E, and S, right? So I have already implemented call and code G, but other functions, for example, you need to write the function encode G and then call the encode O here, and then call encode O, call encode A, call encode G, which is already implemented, call encode G is already implemented, call encode I. So you need to implement encode I and call it. You need to implement encode E and call encode E, and so on, right? Up to S. And then you are returning, right? So now let me walk you through the implementation of call encode G. Actually, let me correct its name so that it is uh, encode G and not something else. Okay. So here, for example, so now when I'm when I'm saying call encode G, so control will be transferred here. And in the body of the encode G, I am calling other what we need to do in encoding G, Morse encoding of G, like character G. We need to have two dash and a dot. So that's why I am calling a function which I have already created and calling it twice, dash function, call dash, and then another function we need to call, which I'm naming as dot. But I have commented this line, I call dot. I have commented it because I have not defined dot. So it is your job to define the dot. I will explain you the implementation of the dash, and then from that and understanding that you need to implement dot function. Okay. So here we are calling call dash, right? So here the function is explained here. So whenever you are defining the function, make sure you are returning from it. And in this function, since we are not modifying any registers other than R16, then we don't need to push them. We don't need to push any registers, and it's fine to not push on R16 because we know that our function, which caller function, which is encode G in this case, is not using R16 anywhere. So it's safe to, even if you don't push it on the stack and pop it from the stack before returning. So what we are doing in the body of the dash, first we are turning on the LED. Remember, we have already here configured LED is in the output port as in the output mode. But here we are writing the value to the output. So we are saying write 1 to the pin number 5 of port B, right? So this is binary. Let me convert it to binary. So the binary will be 0010 0000, right? So here we are saying write 1 to pin 5 of port B, right? You can count from here 0, 1, 2, 3, 4, and 5. Okay. And then we are loading this value into R16 and then writing it on the output port, which is 0x05, is the address of 0x05 is address of port B register. Okay. Port B data register. Okay, and after that we are saying, okay, wait for so since we are representing the dash by turning on an LED for a longer amount of time. So after turning on the LED, we are going to wait for 1 second or 1000 milliseconds. So that's why I am calling the function which I have already written, and it is call wait 1000 milliseconds. So, and then I will explain the body of that function later, but let me first complete this one dash function, right? So after waiting, so it will wait for 1 second, and after that we will turn off the LED, and by writing all zeros in R16 and then sending it to the so we can actually comment it here. Write 0 to pin 5 of port B, and 0x05 is address of port B data register. So now our LED is turned off, and then we wait for 250 milliseconds again before going back to the color, right? So now what will happen, that you will have this LED which turns on and stays on for 1 second, and then it turns off and stays off for 250 millisecond. And then the next function, whatever is in your program sequence, for example here it is call dash again. So again what will happen, that the LED will turn on for 1 second and then stays off for 250 milliseconds. So in this way we have sent two dashes, right? So now let's have a look at the body of this function, call wait 1000 milliseconds. So here is the body of wait 1000 millisecond. Now you can, when you convert 1000 to hexadecimal, you get this number. Now remember that we need to load this value in the registers R22 to R25. Although we are not using these registers anywhere in our program, but still just to practice it, we can push these registers before we modify them in the body of this function. So we push all four of them to the stack, and then we write the value of the lower 8 bits, our least significant byte in R22, load immediate, and then that 03 in, sorry, and then we put 03, which is the next byte, in R23, and then remaining bytes are 0, so we put all zeros in R24 and R25. So why we are doing that? To pass the parameter to the delay function to tell it that how long you need to wait. So actually we are telling delay function that you need to put a delay for 1000 millisecond, and then when we call the delay, it will insert a wait or a delay of 1000 millisecond, and after that the control will come back, and we are popping all these four registers from the stack in the reverse order. Okay, so let me put here just a empty line to indicate to make the code more readable, and after that we return back to the caller. Okay, so when we go return back to the caller, so it's mean we reach here in our dash function, and then it will turn off the LED, and then it will after turning off, it will call this function wait 250 millisecond. Now if we look at the body of this function wait 250 millisecond, everything is same, exactly same as wait 1000 millisecond, with the only difference that we the hexadecimal of 250 is different, so that's why we load different values in R22 to R25 register. Everything else otherwise is same. Okay, so, and then at the end we call return. So which means we go back to the dash function again, and we are done. Now dash function calls the return. So we go back to the caller of the dash function. So who was the caller of the dash function? Caller of the dash function was encode G, right? So now we are done with showing one dash on the LED, and then we call dash again to indicate the second dash, because G has the most code of dash, dash, and dot. And after that we will call the function called dot. However, this function is not implemented, and it is your job here to do, you need to complete this to implement the dot function. I have given you like comments here, a pseudocode, which is what you need to do is you need to turn on LED, then wait for 500 milliseconds, and turn off LED and wait for 100 millisecond. Note that this function for waiting for 500 millisecond is also not implemented, so it is also your job to implement this function. And at the end of the file, here I have mentioned it that you need to write a code for the body which waits for 500 milliseconds. Okay. Uh, yeah, actually, yeah. Okay, so once you have implemented that function which waits for 500 millisecond, and you have also implemented the dot, then you can uncomment this line, this one, and then you are done with encoding G, right? But this is like your to do three. So this is the third task you need to, like third subtask in task one, which you need to do. So you need to call the function dot in the body of the encode G, and then in the similar way, just like you are calling the function encode G to create Morse code for character G by sending dash dash dot, you need to write functions for encoding O, encoding A, encoding I, encoding E, and encoding S. That is to do number 4 to 8. So once you are done with that, the next thing you need to do is that here you need to perform the to do number 9, which is you need to call the functions for encoding. So you have defined those functions here, and now you need to call them in within the body of encode Morse. Okay, just like we are calling encode G. So here you need to sorry, here you need to call encode O, encode A, encode G, and so on. Okay, and once you have done that successfully without any errors, then you are done with the task one. Okay, so I have already completed this task, so let me just show you that once you have written the code and everything is fine, then what you will see on your Arduino board. So let me close this one and open the solution for task 1 lab 4. Yeah, this one. Yeah, and yeah, let us first simply compile our code to make sure there are no errors. Yeah, so I mean, I have written the code, and we don't have any errors. All the to-dos are completed. So now what I can do is like I can connect my board, and I can uh okay, so boards and tools are selected correctly. So now I can run the code or download the code on my board. And here this my green LED is connected with pin 13. So you can see now it is generating the Morse code for Go Aggies. If you want, I can reset it. Let me reset. Yeah, now here dash, dash, dot, dash, dash, dot, dash, dot, dot. So you can follow that. You can check that it creates the Morse code correctly for Go Aggies. Okay. Or I can show you again if you want from here. So let's like reset dash dash go. So dash again dash, right? So we are done with G and O. So you can verify for other characters as well. So this is what you need to do for task one. And after encoding, what you need to do is that you need to make sure that you are creating the correct Morse code, and then show your results to the TA to get points. If you don't show you to the TAs, you will not get points.